Hey kids, Mr. Murray here. I'm Mr. Murray's Mathland, and we are continuing on with some implicit differentiation kinds of problems and applying it to kind of a classic calculus question, writing the equation of a tangent line. So let's just jump right into this and see how we can use what we already know, coupled with what should be kind of new implicit differentiation to get the job done here. So number one here, write an equation for the line tangent to y equals sine of 3x plus 2y, the line tangent to that at the origin. So of course the origin is just another way of saying the point 0, 0. And as always, when you write the equation of a tangent line, you need two things, right? You need the point and you need the slope. And I got the point now, x and y, 0, 0, and my slope is going to come from the derivative, right? So our equation is this, and we're going to take the derivative because that's what's going to give us the slope of the tangent line. So I'm going to take the derivative of this with respect to x, right? And the derivative of each side here, and so the derivative of y with respect to x is dy dx equals, and on the other side, derivative of sine of something is cosine of that same quantity, 3x plus 2y, multiplied by the derivative of the inner expression, right? That's just using the chain rule. It just so happens that the inner expression has x's and y's in it, so this is where you need your implicit differentiation. So the derivative of 3x times 2y is the derivative of 3x, that's just an x expression, that's 3, plus the derivative of 2y, that's 2 dy dx. And so right there, notice of course I had to use parentheses or brackets of some kind around it. And so right here, you've again got these kinds of things that pop up with implicit differentiation where you've got dy dx on both sides. And by the way, there are some people who will, instead of writing dy dx, will just write y prime as shorthand, and right here would write y prime. And that's totally fine. I have no problem with that. But I really like to develop the comfort with this notation, because as we move along, the variables won't always be x or y, and there might be more than two variables in a problem. There's going to be radius, there's going to be time, there's going to be volume. So I like to really be, good with the fundamentals of using this notation. So that's why you're going to see me stick with that for the most part. But now we've got to isolate that dy dx, and we've got one here on the inside of this set of parentheses, and I want to get my dy dx's collected on the same side so I can factor it out. So I'm going to use a little, just algebra from here on out. Just going to distribute this to the inside here. So I'm going to have dy dx is equal to, when I distribute that to the 3, I'm going to have 3 cosine of 3x plus 2y. And when I distribute that to the 2 dy dx, I'll have plus 2 cosine of 3x plus 2y dy dx. I just happen to like writing dy dx at the end. And now you're going to subtract that quantity, bring it over to the left side. So I'll have this dy dx minus this whole term. So minus 2 cosine of 3x plus 2y dy dx equals 3 cosine of 3x plus 2y, right? We're having a dy dx party on the left side, and if you don't have dy dx, you're not invited. It's kind of sad, but those are the rules. Now we're going to factor out dy dx, and just be careful with your algebra. That's 1 minus 2 cosine of 3x plus 2y is equal to 3 cosine of 3x plus 2y, and now I'm going to divide by that quantity. So now I have dy dx is equal to 3 cosine of 3x plus 2y divided by 1 minus 2 cosine of 3x plus 2y. Okay, there's our derivative. Good little practice there, getting dy dx, but why in the heck did I want it in the first place? Because I wanted to get the slope at the origin, so the slope at the point 0, 0. So right, I get the derivative and I plug in my point of tangency. And with these implicit problems, often your derivative is going to have x and y in it, which means you've got to use the x and y coordinate of your point of tangency. So if you don't know the y coordinate, sometimes you might have to get that first. So here we go. And trying to be good with my, Leibniz notation here, dy dx, to show that plug-in. Draw that, vertical line, and you can write 0, 0. Some people write x equals 0, y equals 0 to really drive that home. And now I'm plugging in 0 for x and 0 for y. So that's going to be 0 plus 0 on the inside of that cosine. 1 minus 2 cosine of 0 plus 0 again. And from here, again, if you can do certain things in your head, that's fine, but just be careful you don't make a silly mistake. So this is 3 cosine of 0 over 1 minus 2 cosine of 0. And so we've got to use a little unit circle action here. What is the cosine of 0? If you have to remind yourself, 0 is here on the unit circle. We're talking about the angle of 0 radians or 0 degrees. And the coordinates at that point are 1, 0. Remember that the x coordinate is the cosine, y coordinate is the sine at that spot, right? So c before s, x before y. So the cosine is 1. The cosine of 0 is 1. So that means we have 3 times 1 divided by 1 minus 2 times 1, or 3 divided by 1 minus 2, which is negative 1. And so we have negative 3. And what is that negative 3? That is our slope of our tangent line. Remember, our point is the origin, 0, 0. So write in the equation of that tangent line, if you want to strictly use point slope form, y minus 0 equals the slope of negative 3 times x minus 0. That would be perfectly acceptable. You could also just simplify it to something like that, or some other equivalent version. But there is our tangent line. Same idea. Get the derivative, plug in the point to get the slope at that moment, and write your tangent line. It just became a little more complicated to get there. So if you have any questions, please ask and keep working hard.